And then is the corollary 2 that states that if A is an m by n matrix and C is an echelon matrix which is row equivalent to A. Again, C is obtained from A by applying the row operations. Then non-zero rows of C forms basis for the row space of A. Not row space of C, that is obvious, but it forms the basis for row space of A also, right? So this we need to prove. So proof will almost complete proof is same as in for the previous corollary 1, right? So let's start with the proof. Now since C is obtained from A by applying the row operations, so therefore there exists a non-singular matrix P such that this C is obtained by multiplying P with A, right? So thus row space of C is equal to row space of PA. This is the result I have used over here, and this row space of PA is further equal to row space of A. This is again another result for the non-singular matrix P. So the reason is as P is non-singular matrix. Now suppose that the C consists of R non-zero rows, right? Let's say it is consisting of R non-zero rows. Because C is in the row echelon form with R non-zero rows, so therefore the first R rows R1, R2 up to RR of C spans row space of C. And second, required to prove that these rows are linearly independent. So let's define C matrix to be equal to Cij. This is your row echelon matrix and it is having m by n dimension. That is, number of rows are m and number of columns are n, like before, right? So let alpha 1, alpha 2 up to alpha r, these be the column indices of the leading entries of the non-zero rows of C. And then we need to define CILK, that is equal to 1 if I is equal to k, and this is equal to 0 for I not equal to k. And this is also denoted as Kronecker symbol, that is delta ik. And then let's write the linear combinations of the rows, the non-zero rows having the scalars alpha 1, alpha 2, alpha 3 up to alpha r, right? Then writing this in the summation form, I going from 1 to r, alpha I, ri. Because ri is the ith row and it is having the elements as, yes, C ith row first column, then C ith row second column, up to so on element present in ith row nth column, because number of columns are n. We have defined here that C is the matrix of the form Cij m by n. These are the number of columns and these are the number of rows. So that is why the last element C is present at ith row nth column for ith row, right? So this is equal to 0. And now I am writing this Ri to be as, yes, Cij, right? For j equal to 1, 2, 3 up to n. And then the summation I going from 1 to r alpha I. Then we have defined this CILK, yes, so writing this as CILK. This is equal to 0 as these holds for j equal to L1, L2 up to LR. Then further this is the summation I going from 1 to r alpha I, and this is your Kronecker symbol delta ik, where this k is defined to be as from 1 to r, and here also we should write the condition for k to be as k is from 1 to r, right? And now this is non-zero when I is equal to k, so alpha I should be zeros for I equal to k. So this implies for I equal to k, alpha k is equal to 0 for here k is from 1 to r, right? So this implies alpha 1 equal to alpha 2 equal to alpha 3 up to alpha r, all are equal to 0. And then because all these scalars alpha 1, alpha 2, alpha 3, alpha r, all these scalars are 0, so for this linear combination R1, R2, R3 up to RR, these are all linearly independent. So this implies R1, R2, R3 up to RR are linearly independent. And because these are linearly independent, also these also spans row space of C. So all these forms the basis for row space of C, right? So thus this complete set is a basis for RC. But if I mark this result as star, so from star we say that if those non-zero rows are the basis for RC, then all those non-zero rows are also the basis for RA, that is the row space of A, because these two are equal. So but because row space of C is equal to row space of A, so therefore R1, R2, R3 up to RR, these are the basis for, yes, row space of A. Hence the result is proved. Okay, thank you.